Mr. Harridan here.
Hello, anybody home?
Yes, we are here and home and doing fun stuff like covalent molecules of properties and polarity of covalent molecules. Okay? So this brings up my favorite conversation of all, one of them, just one of them, where I get to discuss polar and nonpolar with you. Okay? So we have done polarity of bonds. Remember, if the electronegativity difference is less than 0.3, it is a nonpolar bond. Now, I should have got some like James Bond clips for this stuff. Next time, Mr. Harridan. If the electronegativity difference is between 0.3 to 1.7, it is polar covalent bond. But now we have to consider the molecule. Okay? There is a difference between the molecules and the bonds. Bonds are only talking about one line there. Molecules, you have to consider the shape. For nonpolar molecules, the shapes are symmetrical. Okay? That is what happens for nonpolar molecules. Which means your dipoles cancel. So you have one dipole point this way, and you have an equal dipole point this way. Okay? That makes it nonpolar. They are symmetrical around the atom, meaning there is no pole. One molecule does not have a higher electron density than any of the other ones. It's just evenly distributed. Okay? Page 15. Oh, we need a sound effect for this. Let's see what science. How about got my homework?
Got my homework finished, McFly?
No, I don't. Okay, so given the nonpolar covalent molecules have the following properties. They have the lowest melting and the lowest boiling points. Most of these are liquids and gases because they're covalent compounds. They do not conduct electricity in any state. Okay? They are insoluble in water, but nonpolar is soluble, meaning it dissolves, in oil. Okay? They exist as molecules sharing electrons, not ions. Okay. Now this brings up to my next one here. Hey, do I got something else about homework in here? I thought I did. Oh, here it is. Ready?
Do you realize what would happen if I handed my reports in your handwriting?
Called academic dishonesty, and you get a referral. Anyways, the next ones are polar molecules. Okay, these are ones with uneven electron density. These molecules are asymmetrical. Okay? Meaning you're going to have like a dipole going this way, and then you have like a small dipole going that way, making the overall molecule being polar. Just so you know. Okay? Their melting points and boiling points are higher than nonpolars. Nonpolars have the lowest boiling points and melting points. Polars are a little bit higher. They are liquids at room temperature. They do not conduct electricity at any state. Okay, they are soluble in water. So polar is soluble, meaning it dissolves in water. That's very important to know. Okay, they exist as molecules, meaning they share electrons, not as ions. Okay? The presence of polar bonds may or may not cause the molecule to be polar. You have to ask question, determine the point. Does the molecule look all the same way around the central atom? If the answer is yes, that means the molecule is nonpolar. If no, that means the molecule is polar. Just so you know. Okay? So, here are some questions that you need to ask yourself. Are all four sides have the same element? If they have the same element, it is nonpolar. Three sides have one element, and the fourth side has a different element. Most likely it is a polar molecule. Okay? Some sides have an element, and the other sides have non-bound electron pair. Most likely it is polar. So here's what this is here. Notice that these are the electronegativities here. Remember that these are in the reference packet. There is an overall dipole towards this chlorine here. There is an overall dipole in this chlorine here. There is an overall dipole to this chlorine here. And there is an overall dipole to this chlorine there. Okay? Remember that this is tetrahedral. How do I know it's tetrahedral? Because it's an AB4, of course. You do know that, right? Of course you do. But the big thing here is that the dipoles cancel. If the dipoles cancel, that means that this is nonpolar. Okay? There you go. Over here, this is also a tetrahedral. This is also AB4. Okay? But here, this one has two different elements bonded to the carbon. There's some chlorines pulling here, some chlorines pulling here, and some chlorines pulling here. And then there is a little dipole of this carbon pulling down this way. So there is an overall dipole downward. If there is an overall dipole, that must mean that the molecule is polar! Just in case you didn't need to know that. Okay, we went over the likes and dislikes thing. Let's go over some examples here and see if we can figure out what's going on with this. How many polar bonds are in CF4? Is the molecule self-polar? Would it be most likely soluble in water and oil? So the first thing we're going to do here is the bonds. To do the bonds, you have to do the electronegativity difference. Okay? So we are going to do the electronegativity difference between carbon and fluorine. This is 4.0 for fluorine. Remember, these are in the reference packet. If you need them on the test, they will be listed in the problem. And there's an overall dipole area that way towards the fluorine. When you subtract 4.0 minus 2.5, you get 1.5, which is in between 0.3 and 1.7. That must mean that this is a polar covalent bond. And there are 4 polar covalent bonds. Now we have to do the shape. Okay. Of carbon tetrafluoride. Fluorine has 7. 7 times 4 is 28. Plus 4, we're going to draw 32 valence electrons. Which one's in the center here? Carbon is the least electronegative of these. So carbon goes in the center. So this goes 2, fluorine, 4, 6, 8 for my 4 fluorines, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay. Stop, collaborate, and listen. Check to see if the octet row you're dissing. You're not dissing here with the carbon, so we're good. So this is a tetrahedral, remember? Tetrahedral. Tetrahedrals can be polar or non-polar. Let's see what this one is. We have a dipole going this way for this F, and we have a dipole going this way for that F. we have a dipole going up, and we have a dipole going down. You want to say hello, Miss Vondercheck?
Hello, polar.
That was a little weak. But it's all good. But overall, all these arrows, these dipoles, cancel. If the dipoles cancel, that means that this molecule is nonpolar, which means it's soluble in oil. Okay, on to the next two examples here. Here we go. Carbon dioxide. Everybody loves some great carbon dioxide, I know. How many polar bonds are in carbon dioxide? So we have to do the bonds first. We have to do the electronegativity difference. Okay? So we have a carbon bonded to an O here. We know the electronegativity of oxygen is 3.5 and carbon is 2.5. You know that from your reference packet. 3.5 minus 2.5 is 1.0, which means that this is a polar covalent bond. I'll come back and tell you how many bonds there are in a second here. Okay, here we go. We gotta draw our carbon dioxide here. So now we have to do the shape here. Okay, so we're doing CO2. Oxygen has 6. 6 times 2 is 12, plus 4 is 16 valence electrons. Okay, so we have our carbon. We're going to bond that to our O, and we're going to bond that to our O. So that's 2 and 4. 6, 8, 10, 12, 14, 16. Then we stop, collaborate, and listen. Check to see if the octet rule you're dissing. Guess what? You're dissing here. This is what we would call an incomplete. Wah, wah, wah. So we have to take this pair here, and we have to take this pair here, and we're going to move them inside to make double bonds here. So it really looks like this. Whoops. Ooh, almost forgot a pair there. There we go. There we have the complete octet. Okay? Because we cannot have an incomplete octet for the center if it's carbon beyond. Of course not. Nobody would ever do that. Right, Miss Vondercheck?
That is correct, Mr. Arcaro.
I know.
Nobody would do that.
Nobody, right?
Not in their right mind.
Yeah. Okay. So now we got to figure out if this is polar or non-polar here. So we have a dipole pulling this way, and we have a dipole pulling that way. Okay. So that these dipoles cancel, meaning that this molecule is non-polar molecule. Okay. Last one we have to do here. How many polar bonds are there in ammonia, NH3? Is the molecule itself polar? Would it be soluble in water or in oil? Here we go. So we have to do the bonds first, right? We have to do the electronegativity difference. So we're doing, oh, I forgot to go back and do the number of bonds here. Okay. You can count this as 2 double bonds, but I'm just going to count it as 4 polar covalent bonds, which are 2 double bonds. Either way. Okay. So we're going to do a nitrogen and a hydrogen here. So this is a 2.1 here. The nitrogen is 3.0. So we do 3.0 minus 2.1. This is 0.9. 0.9 is between 0.3 and 1.7. So you know what I'm going to say here in a second, don't you? This is going to be some polar covalent bonds. In fact, it's going to be 3 polar covalent bonds. Okay. Now we have to do the molecule. NH3. So we have 8 valence electrons here. Okay, so we have a nitrogen bonded to a hydrogen, bonded to a hydrogen, bonded to a hydrogen, and then we have a pair of dots there. Okay. So this time the dipoles are towards the nitrogen, so they're actually going inward like this. So we have these two dipoles that cancel like that. But there is no dipole going this way for this one. We do know NH3 is an AB3E, right? Which is a trigonal pyramid. I know we know that. But the big thing here is we have an overall dipole, which is going down. Oh no, my ink is running out on that pen. I must have used it too much. Maybe that's why they left the pens in my room, because they were used too much. But we have an overall dipole here, which means that this must be a polar molecule. Okay? As a tip for you here, all bents and tripyramids are polar. Or as I like to say, polar! Okay. Guys are champions. The legend.